Good day everyone, my name is Jedi Castro from DCPET 31, and today we're diving into a topic that's transforming the world of electronics and power technology, the future of semiconductors with two groundbreaking materials, the silicon carbide or the SiC and gallium nitride or the GaN or GaN. These two wide bandgap semiconductors are paving the way for more efficient, powerful, and heat-resistant technologies across a range of industries. They're especially important in areas like high-performance computing, electric vehicles, and industrial automation, where demands for power efficiency and durability are at an all-time high. So in this video, we'll explore how these materials work, what sets them apart from traditional silicon, and what all of this means for the future of computer engineers. By the end, we'll have a better understanding of why silicon carbide and gallium nitride are making headlines and the immense potential they hold for the next generation of electronics. First, let's talk about how these new semiconductors might affect or impact the development of more sophisticated and efficient computers. Since we all know that silicon has been the standard for decades, but it's reaching its physical limits as we keep scaling down component sizes. With these limits, we see challenges like overheating and energy efficiency. Here's where silicon carbide and gallium nitride comes into play. Both materials fall under a category called wide bandgap semiconductors, meaning they can operate at much higher voltages and frequencies without the heat issues that silicon faces. Now, imagine a computer chip built with silicon carbide. Its wide bandgap allows it to function under high power and temperature conditions that would overwhelm traditional silicon. This makes silicon carbide and gallium nitride ideal for high power or high performance computing applications that demand consistent energy efficient power over long periods. Computers using these materials could also handle more intense processing loads without generating as much heat or requiring massive cooling systems. Essentially, silicon carbide and gallium nitride could enable devices to handle complex computation faster and more efficiently, taking us further than what Moore's law predicts. As a result, we might see everything from AI processors to quantum computing systems benefit from these materials, allowing them to operate at higher speeds without bottlenecks related to heat and power. Now, let's look at the impact of SiC and GaN technology on electric vehicles or EVs and automation. These materials are not just improving efficiency, they're revolutionizing these fields. For instance, in electric vehicles, silicon carbide has shown remarkable benefits. In 2018, Tesla integrated silicon carbide-based inverters into the Model 3, which allowed a major component of the EV to shrink in size and operate more efficiently. This shift means that EVs can reduce power loss, which in turn helps extend driving range. By using silicon carbide in power electronics, EV or the electrical vehicles manufacturers can design cars that don't need as many bulky cooling systems, reducing the vehicle's overall weight and cost, and ultimately making electric vehicles more competitive with traditional internal combustion engine cars. And in automation, silicon carbide and gallium nitride are essential for devices requiring high power and fast switching capabilities. Robotics, for example, can benefit from the stability and heat resistance of silicon carbide in power electronics, allowing these systems to run longer without overheating or frequent maintenance. Gallium nitride, on the other hand, is especially suited for applications needing high power density such as wireless charging and high-speed data transmission in 5G networks. By incorporating these materials into power electronics, industrial automation systems becomes more efficient, can run at a higher power levels, and have lower energy consumption. This shift toward bandgap semiconductors in EVs and automation marks a significant step forward in both energy efficiency and sustainable technology. So, asking the question, what makes silicon carbide and gallium nitride so advantageous compared to traditional silicon? Well, the answer lies in their physical properties. Both silicon carbide and gallium nitride are known as wide bandgap materials, meaning they can operate at higher voltages and higher frequencies and extreme temperature while maintaining efficiency. Silicon, on the other hand, has a narrow bandgap, which limits its performance under high power or high temperature conditions. One of the standout benefits of silicon carbide is its ability to handle temperatures up to 300 degrees Celsius, which means devices using SiC or silicon carbide can manage more power without overheating or breaking down. Another big advantage of the silicon carbide and gallium nitride is their efficiency in power conversion. Silicon carbide can reduce power losses significantly, which is why it's a favorite for applications like the electrical vehicles and renewable energy system. This efficiency then translates into less energy wasted, as heat and more power delivered to the system. Gallium nitride is similarly efficient, though it tends to be used in lower voltage applications like chargers and power adapters and wireless communication devices. The gallium nitride has made it possible to develop ultra-fast chargers for mobile devices and even wireless charging solutions that generate less heat and charge faster than silicon-based charger. So overall, these materials offer efficiency, durability, and adaptability, setting them apart from traditional silicon. Finally, let's discuss what all of this means for computer engineers like me and their careers. As silicon carbide and gallium nitride are gradually integrated into more industries, the demand for engineers who understand wide bandgap semiconductors technology will rise. Computer engineers who work in hardware design, power electronics, or energy systems will especially find themselves in high demand, as this shift requires a solid understanding of these materials and how to design circuits, processors, and systems that fully leverage their capabilities. For computer engineers, this trend toward silicon carbide and gallium nitride means new learning opportunities and the potential to work on cutting-edge projects in electric vehicles, industrial automation, and high-performance computing. Engineers with expertise in this next-generation semiconductors could lead projects focused on improving power efficiency and sustainability across technology sectors. In short, the future of computer engineers, or the future for computer engineers, looks incredibly promising, with silicon carbide and gallium nitride opening doors to innovative applications that were once limited by traditional silicon. Staying informed and skilled in this technology will be the key for those looking to make an impact in the evolving semiconductor industry. So in conclusion, silicon carbide and gallium nitride are truly fascinating materials that are changing the landscape of electronics. Their unique property gives us a glimpse into the future of technology, from more powerful computers to greener transportation and efficient industrial systems. So, if you're interested in exploring more on how these semiconductors are shaping the tech industry, be sure to always be notified and knowledgeable about this technology. That's all. My name is Jedi Castro from DCPET 31. Thank you all for watching.